Okay, so for part 2 of homework 7-1 here, we'll pick up with question 7. So question 6 in the previous part gave us a function for the angular velocity. This one gives us a function for the angular acceleration, right, in terms of time. So they give us 45t squared, or t to the third, excuse me, and then minus 11t to the fourth. I wish it was t squared. That would make it a little easier to integrate, but we'll see that here in just a second. Anyway, they say if it starts the wheel, if the wheel starts at rest at 0 seconds, when is the next time that the wheel is at rest again? Well, they're talking about when is it at rest, right? Which means we should be thinking when is the velocity equal to 0. So in order to do that, well, I need to integrate my acceleration function, right, to get my velocity. I know my velocity is the integral of the acceleration. So I need to integrate this function, and that unfortunately is where it does get a little bit tricky. So when I integrate this function, it just, not even tricky, it's just messy, right? So 45 divided by 4, t to the fourth, and then minus 11 divided by 5, t to the fifth. And obviously I could find decimals there as well, but I'll go ahead and leave it like this for right now. It would have a plus c, but they told me that it starts at rest when the time is 0. So if I plug in 0 for t, so I'd have 0 on the left-hand side because it's at rest. And then if I plug in 0 over here, I'd have 0 minus 0 plus c, and so that does tell me for sure that c is also 0. So anyway, I've got this function then, right? I've got my function for the velocity. So I'm going to go ahead and maybe make that 11.25 t to the fourth minus 2.2 t to the fifth, and then again plus 0, so I don't need that in here. And they're asking me, when does the wheel come to rest again? Well, it's going to be at rest when, again, the velocity is equal to 0. So I'm going to set this whole function equal to 0. So I've got 11.25 t to the fourth minus 2.2 t to the fifth. And in order to figure out when it's going to be at 0 again, I really just need to figure out then what are the zeros of this function, right? So I need to solve for t. Well, it looks worse than it is, right? I know some of us are thinking maybe graph it, but if you just go back to factoring, right, what's the most that I can factor out of both of these? Well, I can factor a t to the fourth out of each of those. And the reason that's helpful is then I get 11.25 minus 2.2t, right? And so where do the zeros occur? Well, 4 of my zeros occur at 0, right? I get t equals 0 4 times from this. So 4 of the zeros happen at when t equals 0. The other one's going to happen when this parenthesis is equal to 0. So 11.25 minus 2.2t, I just need to set that equal to 0 and solve it, right? So obviously subtracting 11.25 over, dividing by 2.2, and I get the time equals about 5.11 seconds. So again, the time equals 5.11 seconds. So that's when it returns to rest once again. Question 8, at first the diagram looks kind of complicated here, but if you actually take your time with this, I think you guys will agree it's not too bad. So we've got this light triangular plate in a horizontal plane, light indicating we're not worried about like the mass of the plate itself. 3 forces act on that, which is pivoted about a vertical axis through point 0 down here, so through point O probably. If the figure, right, in the figure F2 is perpendicular to OB, so F2 is perpendicular, and then consider the counterclockwise sense to be positive. What is the sum of the torques about the vertical axis through this point? So I'm looking for the sum of the torques through that point. And the reason I said this actually isn't too bad. So if I'm looking for my net torque, right, what I'm really looking for then is the torque caused by the first force, so the torque caused by F1, plus the torque caused by F2, plus the torque caused by F3. Well, if I look here at starting with F3, since that force is acting directly at that axis of rotation, you can think of the radius as being 0, right? So this isn't going to produce any torque at all. So that third force, which is off at the angle there, don't even have to worry about that. It's not going to produce any torque. So the only two that are going to produce a torque are T1 and T2, right? And while we're here, let's think about the direction. So F1 is going to pull it off this way, and again, if this is my pivot point, then F1 would cause it to rotate in the clockwise direction, right? It would go around clockwise. So F1 would actually be a negative torque, and then F2, which is causing it to pivot this way, would cause it to rotate in the counterclockwise direction, so a positive direction there. So again, all I really need to do is find those two torques and then find the sum of those two. Right, so to find torque 1, well, T1 would just come from, again, the part of the force that is perpendicular to the axis of rotation. So it's coming from force 1 times the radius, and then times the, in this case it'd actually be the cosine component of that angle. I know usually we use sine, But based on the 30 degrees, I actually would use the cosine component, because that would be the component of the force that is perpendicular to my lever arm. Right? So at this point, though, I know all of those measurements. It would just be, again, a negative 6.0 times the radius, which is 0.60, and then times the cosine of 30, and of course make sure you're in the right mode, make sure you're in degrees and not radians. But anyway, we can calculate that number. The torque caused by the second force is much easier because there's no angle involved. So it's just going to be the second force times the radius of that motion, right? So the second force, which they told me up in the problem above, which is 9 newtons, so 9 newtons, and then the radius that it is away, we can see there the 0.80 meters, so we've got that measurement to work with there. So I'm just again finding the resultant of those two torques. I'm taking those two torques and adding them up, and when I do so, I end up getting 4.08. It is a positive 4.08 newtons meters, right? So there is the net torque acting on this object in the horizontal plane. So like I said, at first it looks kind of complicated, but hopefully in the end not actually that bad. So then the last two questions here of homework 1 are pretty much just review questions of torque to make sure you're pretty comfortable with it. Okay, so the key on these questions, as always, is usually choosing the right pivot point to make it easier to solve. So we're looking for tensions in both wire A and B, right? We're looking for both of those tensions, which, keep in mind, those are forces. And then they tell us the mass of the beam. They give us the weight of the block that's on the beam, so we've got all of those forces at play too. So when I think about this problem, right, the first thing I always want to do is I do want to think about the forces involved. So again, I have tension A pulling up, I have tension B pulling up, and then I have the two forces of gravity, one acting from the middle of the beam, right, the force of gravity of the beam itself, and then I've got the force of the block on there. I'll call it FGM, the force of the mass pulling down from over here, which is 2 meters from the right. So these are the forces. And if I start with just forces, I know that sum of my forces, the total sum of forces, needs to be 0, because the beam is not accelerating upward or downward, right? I know the beam is in equilibrium, so its sum of forces needs to be 0. So that tells me then that tension A plus tension B needs to equal those two forces of gravity, right, collectively. So those two forces of gravity both pulling down. The problem is right now, even though I know both the forces of gravity, since I don't know either tension, I don't have a means to find the other one. And unfortunately, I cannot just say that they split it evenly, because since this block is not right in the middle, then they're not going to evenly distribute the total weight. So if I start with forces, which I would recommend you do, unfortunately, for this particular problem, we get stuck. And so that's where obviously torque comes into play. So the key with torque is choosing a pivot point that helps us to eliminate one of our unknown forces. And what I mean by that is if I choose either the far left or the far right to be the pivot point, then, so for instance, if I choose the far left, then with regards to torque, the tension caused by this wire A would not produce any torque because the radius would essentially be 0, right? So there would only be 3 forces that would produce a torque. These two forces of gravity and tension B. And so let's go ahead and do that. If I choose pivot, if I choose tension A to be the pivot point, then I've got the rest of this obviously set up to work with. So as I do that, again, the relationship would be the torque caused by the force of gravity of the block, the mass, plus the torque caused by the force of gravity of the beam itself would have to be equal and opposite to the torque caused by tension B, right? These two torques would both be causing it to rotate downward, whereas tension B would cause it to rotate upward, and since the beam is not actually rotating, everything needs to be in equilibrium. So again, as soon as I set this up, hopefully this problem is pretty easy. The nice thing is all of these forces are perpendicular, so I don't have to worry about any angles. I don't have to worry about any sines or cosines or any of that. Right? So this is just the force of gravity of the mass times how far away from the pivot point is it. Right? So it would be 1.5 meters from my pivot point at A. So the force of gravity of the mass, which they told me was 550 newtons, times 1.5 meters, plus the beam itself, which we said was 1,200 newtons in the problem. Right? So the uniform beam itself, and then its force of gravity would be acting from the center, so from 1.75 meters from the pivot point of A, right, half of 3.5. And then that would be equal to the tension B, which I don't know, which acts the entire 3.5 meters away. Okay, so I set this up. Obviously, the only variable that I have in there ends up being tension B. So TB and I can solve for that second tension. And when I do that, I end up getting about 835.7. So my tension in that second wire, in wire B, ends up being about 835.7 newtons. And as soon as I find that, finding tension A is pretty easy. Because although you definitely could do another set of torque, I would actually just take it back up to this equation, right, and use my forces. So if I want to solve for the first tension, I'm going to use these two forces of gravity minus tension B, right? So my force of gravity of the block, 550, plus my force of gravity of the beam, 1200, minus the tension I just solved for, 835.7, and that ends up giving me that tension A is about 914.3 newtons of force. Right? So tension A, tension B, hopefully nothing too tricky to solve here. It does make sense as I reflect back on this problem that tension A should be a little bit higher than tension B, since the mass is located closer to tension A than it is tension B. So anyway, question 9, like I said, hopefully a review question for you, hopefully one that wasn't too bad to work your way through. Okay, so the final question, one of the good old ladder questions that I know we love so much. And again, I did go ahead and write the correct answers down here, so again, if you've got those, you're confident, feel free to move on. I also did make a mistake in part B. It says, what is the upward force exerted by the ladder? It should have been, what is the upward force exerted on the ladder? So in this case, one of the few times where English does matter. You can document me on having said that, but anyway, we do want to make sure we correct that. We're looking for the normal force on the ladder. And let's actually just start with part B. Right, so if I think about the ladder, the first thing that I do want to think about is, what are all the forces acting on this ladder, right? Well, they give me all of the different weights and all that fun stuff, right? So I know the force of gravity of the ladder itself would be acting from the middle. So I have 225 newtons pulling down from the middle. And then I have the, let's see, I've got a 65 kilogram person standing 3 meters up from the bottom. So 65 kilograms times 9.8 would give me their force of gravity, which would be pulling down from over here. So we can certainly calculate that number in just a moment as well. And then what other forces do we have acting? Well, we'd have to have, in order for there to be no torque, right, if I'm choosing this as my pivot point, then there has to be a force up here at the wall that's pushing outward to counteract these two forces of gravity. So I have a force of the wall, call that the force of the wall, so Fw. Really it'd be like the normal force of the wall, but whatever. And then I also have two forces down at the bottom. Right? In order to counteract these two forces which are pulling down vertically, I have to have the normal force pushing up, and I'd have to have a frictional force pulling horizontally to counteract the wall force. Right? So these are the 5 forces that are at play. These are the 5 forces that it's very important to identify. So again, actually, if I start with part B is pretty easy, because if they ask us to find the normal force or the force exerted on the ladder, the normal force is just a matter of looking at my vertical components. The only 3 forces acting vertically are the normal force and the 2 forces of gravity. And since the ladder is not accelerating upward, we know the normal force has to be equal and opposite to those 2 forces of gravity. So the force of gravity of the ladder and the force of gravity of the person. Right, so again, in terms of calculating this, I just have my 65 kilogram person times 9.8 plus the 225 Newton ladder. So calculating those measurements, that's where I got my 862 Newton normal force exerted on the ladder by the floor. So I've got that measurement. So then trying to set this up quickly so we can finish it here in this part, right? In order to find A, what I need to do is set up the torques. And again, I'm going to choose the pivot point as the bottom, right? So if the bottom is the pivot point, that removes the normal force and friction from the discussion of torque. So I have the torque caused by the force of gravity of the person plus the torque caused by the force of gravity of the ladder would be equal and opposite to the torque caused by the force of the wall. And the biggest thing as you're setting this up is paying attention to both the radius and then the sine components of the angle. Right? So if the angle down here they told me was 78 degrees, then each of these angles with respect to the ladder would be 12 degrees for the 2 forces of gravity. So as I set this up, the force of gravity of the person times the radius to the person times again sine of 12 degrees plus the force of gravity of the ladder plus the radius to the ladder, which again is half the distance of the ladder, and then sine of 12 degrees, and then finally the torque of the wall, which would be the force of the wall times the radius to the wall times the sine of 78 degrees. So at this point it's just a matter of plugging in and solving for the force of the wall. When you find the force of the wall, you should end up finding that that is 69.1, and because the force of the wall is equal to the force of friction, that is also 69.1. So the calculation